Okay, so we'll continue with perturbation theory and perhaps do some examples. So let's just remember what you are doing. We have this original Hamiltonian whose solutions, exact solutions, we know. Okay, so we know that we can solve this, obtain the wave functions, obtain the energies, etc. Now, the problem that we are faced with is that if this h now becomes equal to this original h0 plus some h1, and then, of course, it's an eigenvalue equation, and things can get quite complicated, and we do not know what happens. Okay, but we can construct a systematic expansion of the solution. Okay, the systematic expansion of the solution, okay, says that the energy of the system, En, for this new Hamiltonian, can be written as En zeroth order result plus En first order result plus En second order result. Okay, so this will generate, in general, okay, terms to higher orders. Similarly, the wave function is not going to be, okay, psi n 0, okay, so psi n is going to be equal to the original psi n 0 plus psi n 1, okay, plus higher order terms. Okay, now one thing, maybe I'll write one more to emphasize the fact that, okay, psi n 0 we take as normalized. Okay, so these psi n zeros obviously are orthonormal, so they are properly normalized. But when I write my solution like this, you see this is normalized, and I'm adding extra terms to it. Okay, so in general, this psi n is not normalized. Okay, so when you are evaluating averages with respect to this wave function, you have to properly, okay, divide that by psi n inner product. Okay, and also these psi n1, for example, is going to be to contain no component of psi n0. So these psi n1 and psi n2 do not contain the original term. Okay, so they are actually orthogonal to this zeroth order term. In fact, we obtained some results last time. For example, psi n1 was what? Psi n1 was a sum. Okay, I could expand this in terms of the original psi n zeros. Okay, so I can expand this in terms of psi n, okay, psi k zeros as a series, and the expansion coefficient, okay, is such that I have this hkn, or the first order Hamiltonian, divided by En minus Ek. Okay, so you see this does not contain any psi n0. Okay, there's no psi n0 in psi n1, and if you do the algebra, there's going to be nothing also in psi n2. Okay, so this is something that's important and we should keep in mind. All right, so that's our expansion. What do we mean by hkn of this object? Well, that's just psi k0 h1 psi n0. Okay, so it is the matrix element of h1 with respect to the original, okay, exact, okay, psi n0 for H0, right? We also found out what En1 was. That was very easy. Okay, the first order En1 is just H1 and N. Okay, so the diagonal term gives us the shift, first order shift in the energy, and the off-diagonal elements enter into this expansion of psi n1, okay, in terms of the original psi's. Okay, is all of this clear? Any questions? Okay, so let's move on. We are going to look at the second order object. Okay, so the second order object is going to contain two terms, okay, or products of terms which will add up to two orders. Okay, what do I mean by that? Okay, I am trying to write down what H psi is equal to E psi is, but both, okay, so everything here, H and E and psi, okay, are expansions in various orders, zeroth order, first order, second order, etc. So if I just put all of those things in, last time I did it, so let me not write it one more time. Okay, it's just going to be a nice long equation. This is going to be H0 plus H1. This is going to be psi 0, psi 1, psi 2. This is going to be E0, E1, E2, and so on. So I just substitute those terms into this equation. So in second order, what do I get? Well, let's see. I am going to get H0. Okay, so this is, okay, let me be consistent with my notation. H0 multiplied by something second order. So it's going to be psi n2. Okay, you see this is a second order term. There's a 0 here and a 2 there. And then the next term is going to be H1 psi n1. Okay, and that's it for the left-hand side because there's no H2. Okay, because there's no H2, I can't write an H2 psi and 0, right? Now on the right-hand side, I'm going to get a number of terms. So I'm going to get En0, okay, times psi n2. Now this is the second order correction to the wave function. Okay, so it's second order, plus En1, okay, psi n1, still second order, 1 plus 1, plus En2 psi n2. Wait, I'm sorry, psi n0, right? Yes.
Why we did not write H2 psi 0?
Because there's no H2. Okay, H is just H0 plus H1. Okay.
But why we don't have H2?
Because it's our Hamiltonian. Okay, we have H0, and with just H1, we'll have enough trouble solving the problem. Okay, so we don't generate a higher order at each step. In fact, we'll, for example, have problems in which we solve H0 plus H1, and then we'll say, well, why don't we add this interaction also? And then what will happen is that we'll assume that the solution that we obtained with the initial perturbation to be our H0, psi 0, and then just move on with the second term. Okay, so it's a matter of strategy how you solve the problem. Okay, yes.
Why do we have psi 2?
Psi will in general be generated into, okay, so this series when we have H0 and H1, this will generate a set of terms which in general will go all the way to infinite order. Okay, so you can put something just first order into your initial equation, but that is going to generate in general all orders. Okay, so think of this as if you are writing a function. For example, this is an function. The energy is function of this perturbation. It doesn't have to be linear. Okay, if it's a nonlinear function, it's going to have corrections to all orders. Okay. All right. So that's what I have. Now the strategy is exactly the same. I take this whole equation, okay, and multiply, okay, or take the inner product of this thing with psi and 0 again. Remember, when we did that in the first order, we obtained the equation for the energy. Now we are going to do the same thing, and we are going to obtain the energy for, okay, the second order stuff. If we want to find the wave functions, we take a different n, okay, we take a psi k0 and go through it again, but the equation is going to be a little bit more complicated, so we'll not even discuss anything more than second order energy, okay? All right, so now you are going to help me with what all of these terms are. Okay, I have psi n0, h0, psi n2. Okay, so just this one, let's do it in detail. Psi n0, h0, psi n2. What is that?
E0 times psi 0 psi 2.
Okay, and what's that? 0, right? Because there's no contribution in psi n2 from psi n0. Okay, so this thing here is just going to give me E n0 operating towards the left. Okay, psi n0, psi n2, which we said was going to be equal to 0. Okay? So that term is out. Now, then I have this one, which says psi, okay, so that survives, psi n0, okay, h1, psi n1 is equal to, okay, so these ENs are just constants. So what is psi n0, psi n2? 0, right? It's already over here. So the first term is 0. What about the second one? Psi n0, psi n1? Again 0, okay. Unbelievable, but true. Okay. Plus the last one, what is psi n0, psi n0?
E2 or E2.
Yeah, okay. Psi n0, psi n0 is 1, right? Okay, so which remains, okay, so En2. That's very nice. I found what En2 is, right? So what is En2? Let's look at that. En2 is equal to this object here, right? So psi n0, yes.
Isn't this also 0 because h1 operates on psi n1?
No, but this is not an eigenfunction of psi n1. Okay? These are, okay, so you should keep in mind that these h1, h2, etc., okay, no h2 obviously, there's this h1, but psi n1 is not an eigenfunction of h1. Okay, this is something that we just fine, but it's okay, it's not an eigenfunction. Okay, so now we have the h1, and then psi n1, which is right over here. So we can put that in. Okay, so that's going to be k not equal to n of h kn, okay, matrix element of h1, the kn matrix element, en minus ek, and then I have psi K0. All right, so you see psi, this HKN is just a number. Okay, it's the matrix element now. So I can just rewrite this as, okay, so let me just do it slowly. So I'm going to get some K not equal to N of, let me pull out this H1KN over here. So it's going to be En, these are En0 and Ek0, right? Which I should have over here also. These are the zeroth order energies. Okay, so I have En0 minus Ek0. And then, okay, just psi N0 H1 psi K0. Okay, but that's something that we defined over here as the matrix element itself. So I get another matrix element, which is going to be HNK of the first order object. Now, HKN and HNK are Hermitian adjoints, okay, complex conjugates of one another. So their product is just going to be the magnitude squared of this. Okay, so we'll just get, as a result, let me just put it one more time so that we can put it in a box. This is going to be a sum K not equal to N of H first order Kn magnitude squared. Okay, that's nice because I want something that's real as energy, divided by En minus Ek, okay, zeroth order. All right, so this is the second order change in the energy, and we will not really go any further. We will not even look at what happens to psi because it's not too interesting, okay? It's a complicated equation.
I have a question.
Sure.
How do we know that zeroth, first and second order corrections are orthogonal?
That's how we construct them, okay? You see, this is how we construct it. So there's no psi n0 in it. If there's no psi n0, then that's what we get. Okay. So now, what is the structure of this? You see, the first order energy change, okay, is something that depends on this H and N. Okay, so that will correspond to some change. But what happens to in the second order change? Okay, I have these energy levels. Okay, so suppose this is the nth energy level, and this is the kth energy level. Suppose Ek is larger than En. You see the contribution to this energy change from this term is going to be, okay, En minus Ek is negative. So that term is positive in the numerator. So the contribution to this energy change is to be in a negative direction on En. Okay, so the effect of this state near the energy level N is going to will try to reduce this. Okay, so this is En2, we'll try to lower that energy level. Now, if you look at it in reverse, obviously, at some point, I also want how the energy of the kth level is changing, right? So for that case, I'm going to get the opposite, right? If I look at Ek, this is going to be Ek minus En, and then it's going to be a positive term. So the second order change in the, okay, for the kth energy level, Ek2 will be in a direction to, okay, move it away from it. So the effect of the second order perturbation theory is going to be the largest if the energy levels are close to one another, okay? And their effect is to push the energy levels apart, okay? So perturbation theory doesn't like degeneracies. We have not yet looked at what's happening in the case of degeneracies, but you can start to sense what will happen, okay? So degeneracies will be lifted because of additional terms which go into the Hamiltonian. Okay, so that's the effect of the second order change in the energy. Okay, so that's more or less where I'll stop with the formalism in terms of the time independent, non-degenerate perturbation theory, and we'll look at examples. But any questions at this point? Yes.
So, Hocam, only second order perturbations are actually trying to separate energy levels apart, right?
Well, actually, everything starts to separate one another. Okay, so there's this, okay, nice theory which is called the random matrix theory, where you put in lots of random numbers into matrices, and the effect is that even though everything seems to be random, the energy levels try to push, okay, the eigenvalues of the matrix try to push one another apart. Okay, so in general, the more interactions that you put in, the more complications you put in, that has an effect of separating the eigenvalues from one another. Okay. Questions? Okay, so let's do some examples. Okay, we already did one last time. I just put in a straight linear term into the Hamiltonian, and we try to see what happens. But let's now look at another set of interactions. Okay, so again, what I'm going to do is I'm going to put the, okay, so we'll call this an example again. So we'll again put particle in a box, okay, and in order to use the symmetry properties, I'm going to put the origin in the center so that the box extends from minus a over 2 to plus a over 2. Again, we know what the eigenfunctions are. They are either functions which go like cosines. Okay, so they are things which look like 2 over a cosine n pi over ax, or they are sine functions which do something like this. Okay, so this 2 over a sine n pi over ax. Okay, so in order to satisfy the boundary conditions, these are for n odd, and these are for n even, right? Okay, so that's the standard particle in a box type of solutions. Okay, so what I'm going to do now is I'm going to, okay, so this is going to be my H0. Now I'm going to add some perturbation into the problem. And the perturbation that I'm going to add is going to be a very simple one. I'm going to put a delta function potential in the middle of the box. Okay, so this H1, okay, let me just be consistent, H0, this H1 is going to be some alpha times delta of x. Okay? So, what happens to the energies? Okay, how do the energies shift? Well, let's just start, okay, and look at what's happening with En1, right? So En1 is going to be equal to either a cosine squared function or a sine squared function, okay? So I'm going to get either, so let me just put this more generically, okay? So it's either going to be, okay, a sine n pi over a x squared or a cosine squared n pi over a x. Okay, so depending on whether n is odd or even, right? And there's going to be the h1, so that's going to be delta of x. Okay, so this is my h1, and I am finding the matrix elements h and n. So what do I get out of this? Well, okay, so the upper one is for an even, right? So let me put these even and odd. Okay, notation like this. So I am going to get 2 over a integral minus a over 2 to a over 2 of either 0 or 1, right? After this integral, well, there's a dx someplace, and there's an alpha, okay? Let's see. Mm-hmm.
0 or 12. You didn't write the alpha coefficients in front of the delta function.
Where?
Oh, you wrote the right, okay.
I'm a little worried about the units. That's why I'm puzzled. What are the units of alpha? Careful. What are the units of alpha? What are the units of delta function? Hmm? No.
1 over x.
1 over x, right? Because when you integrate the delta function, dx, you are going to get 1. So delta function has units of 1 over length. Okay, so if it's 1 over length, alpha has units of what?
Energy times length.
Energy times length. Okay, so I am trying to, okay, I think we are okay. We have 1 over a here. Okay, so, and no, we are not okay. Oh, we did the integral. Okay, I'm sorry. We did the delta function integral, so the integral is not there. So the result of the integral is either, okay, 0 or alpha. Okay, so it's even or odd. So I'm going to get 0 for even n, or 2 alpha over a for odd n. Okay, so those are the energy levels. Okay, so this says that I'm going to get for odd n, okay, it's a little confusing. For odd n, you have even functions. Okay, for even n, you have odd functions. So I'm going to get some result if the wave function is even. Why? Because the wave function will feel, the particle will feel this perturbation only if the wave function is finite there, right? If the wave function is 0 there, then the delta function, okay, is not being felt. Okay, the delta function is not having a big effect on the wave function, so there's no contribution, at least to first order. Okay. Now, what would I really expect if I wanted to solve this problem exactly? Okay. How would this change? Okay, so I know that in this region, okay, from minus a over 2 to a over 2, I have a sinusoidal function, but because there's this delta function, there will be a break in the derivative. So at this point, there will be a break in the derivative trying to, okay, bend the wave function away like this. Okay, so this is for a small alpha. If I have a bigger alpha, okay, I'm going to get something like this, symmetric, because it's in the center. Okay, so this is a bigger alpha, and if I have a really big alpha, okay, then it's just going to be something like that. Okay, so it's going to separate the wave function into two symmetric pieces.
I have
Yes.
a question. In there, shouldn't it still satisfy the boundary conditions at right-hand side?
Yes. Okay, it still has to, oops, yes. Well, I can't draw my pictures so well. It's supposed to be symmetric and everything. Okay. Okay, let me talk to you about something, because this is an interesting problem. This is not related to perturbation theory or anything, but suppose I have this box, and then I put a separator in between, like this. Okay, so I suppose I take this delta function separator, a wall, and, okay, build up this wall so that the wave function is separated into two pieces. Okay? Now, let me go back to the original problem. If I try to squeeze this wave function into a smaller space, what will happen? Will its energy increase or decrease? Increase, right? Because I'm squeezing it into a smaller space. So its momentum is going to be increasing. Momentum uncertainty is going to increase. So its energies are going to increase, okay? In fact, it will go like 1 over a squared. So as I squeeze it in, the energy is increasing. So it's something like a pressure is being applied to the box, right? I'm doing work, okay, from the outside, squeezing the box in as the energy inside the box is increasing. Okay, so this is a mixture of classical and quantum mechanics, if you like, but basically conservation of energy. I'm squeezing the box in. Now, if I just raise this potential up, okay, that's what happens to the wave function. So this says the electron can be on the left-hand side of the box or the right-hand side of the box. And since it's symmetric, okay, I don't know which side it's in. So if you think of this middle separation now, middle separator, as some sort of piston, which could move left or right, it's not going to move left or right, right? Because I don't know where the electron is. But suppose I make some sort of measurement. I scatter a photon or something. And now I found out that the electron is not on the right-hand side, but it's on the left-hand side. The wave function will immediately collapse to something like that. And now there's a force on this piston. Okay? So what has happened here? Okay, I have this wave function, which is symmetric. Okay? I'm not really moving the electron from one side to another. Okay, just making a measurement. And that measurement now collapses the wave function, which results in some external result. Okay, so I feel like this is an interesting question to think about. So that's all I'll say. You can find some stuff about it on the internet or whatever. It's an interesting problem. In any case, that's our first order energy. Now, this means that, okay, the wave function, if I solve the problem exactly, is doing something like this, right? Now let's see how the wave function is changing in perturbation theory. So we'll look at this object again. So psi n1, remember, is equal to some k not equal to n h, okay, kn divided by e n minus e k psi n dot psi k 0. Okay? So what is the correction to the wave function which comes due to, okay, this h1 with that? Okay, so I have to just find the expansion. Okay, so let me look at the ground state. Okay, so let me look at what psi 1, 1 is. So that's going to be a sum k not equal to 1 of hk1 of the first order Hamiltonian. Okay, e1, 0, I forget the zeros, minus ek 0. All right, what is hk1? So hk1, first order, is going to be two wave functions being multiplied together. So it's going to be 2 over a. Okay, a square root of 2 over a comes from each one of these things. Then an integral from minus a over 2 to a over 2. And then I have hk, which is going to be sine or cosine, I don't know. So let me write both of them. Okay, depending on whether k is even or odd. Sine k pi over a x, or cosine k pi over a x, multiplied by cosine just 1 pi over a x. That's my wave function 1. Okay, and then I am going to get hk1. Then I also have alpha delta of x dx. Now you see, as long as I have the sign here, I'm going to get 0. Okay, so this one is, remember, for even k, and this is for odd k. So as long as I have an even k, I am going to get 0. Okay, so there will be no contribution. Okay, so this is going to be 0 for k even, but for k odd, it's very easy because cosine 0 is 1, cosine 0 is 1, and all I get is 2 over a times alpha for k odd. So now let me go back to my equation for the wave function. Psi, okay, the ground state wave function to first order is going to be equal to, okay, so I'll have to write this. So it's going to be a sum k not equal to 1, hk1, well, that's easy, 2 over a times alpha. And then I have a denominator, which is going to be, I didn't write psi k0 here, which I should have. Okay, I'm just writing this down. So in the denominator, I'm going to get h bar squared over 2m, okay, en, so it's going to be pi squared over a squared, minus ek, which is going to be h bar squared over 2m, okay, and pi squared n squared over a squared, psi k 0. K squared, thank you. All right, so let's simplify this just a little bit more. Okay, so it's going to be, let's see, 2m, well, 4m over h bar squared. There will be a pi squared in the denominator. Please check my algebra. A squared in the numerator, but that will be cancelled by one of these a's. Alpha, right? And, well, I should really put a minus sign.
K odd.
Okay, yes. K not equal to 0, and K should be odd. K not equal to 1.
Why did we add K squared to the energy term?
It's EK.
But n squared, I think, is the correct.
Or for the kth energy level, EK.
Okay.
Okay. Okay, so K is that. So I'll put a minus sign in front so that I'll get something which is positive. So it's going to 1 over K squared minus 1. So K not equal to 1 and also odd. These things can be summed over, by the way, amazingly. Okay, and psi k 0. Okay, so you see, I'm going to get terms here which have contributions only from the odd functions. So my psi, original psi 1, is something like this, right? So this is my psi 1, 0, which looks like this. Okay, in fact, let me just write it as a function rather than a ket vector. So this is just psi 1, 0 of x, right? Now, there will be contributions only from odd k's. So it will try to approximate this as much as it can in the first order. So it's going to this, I am going to add something which looks like this, okay, with a minus sign, okay, minus cosine. So what it will do is when I add them up, it's going to, okay, reduce this central part a little bit. Now, if you add the second order, third order, fourth order, if you could do it all the way to infinite order, hoping that it converges, then you are going to get something which looks like that, okay? Sometimes it doesn't converge, okay? These things are, okay, it's a complicated expansion, and you have to be careful. All right, so I hope you get the idea. We have these things, okay, these objects which are, which we can use, okay, term by term to obtain better and better approximations to the actual solution. Okay, perhaps one, okay, let me just start another problem.
I have a question.
Sure.
The derivative of here. The derivative must have a discontinuity of magnitude minus alpha.
Okay.
But in here, the derivative changes from negative to positive.
Okay, so if you do the algebra carefully, you'll see that it has to do it that way for a positive delta function.
Oh.
Okay? It's a good thing to check, but okay, it will be that way. Okay, let's look at another problem. Suppose now I put in 2 particles into the box. Okay, so again, so let me call this example again. I suppose I have again the same problem, minus a over 2 to a over 2. Okay, and this is my origin. Okay, infinite box. I'm not going to write the functions again. Okay, but suppose I put in 2 non-interacting particles into this box, into the, say, ground state. Okay, what will happen? So 2 particles in the ground state. So that means my psi is going to be equal to, okay, so this is going to be my psi 0th order state, okay, ground state, both particles, so I should really put 1, 1, right? That's going to be 2 over a, product of these 2 functions, cosine pi over a x1, cosine pi over a x2. So it's a symmetric function. So if they are fermions, they have to be in the singlet state. So the spins have to be anti-symmetric. But the space parts for these 2 are that. And I have a certain energy because I have 2 particles in the same state. It's just going to be twice the ground state energy, right? Now, suppose I am going to, okay, so this is again my H0. Now, suppose I put in an H1. Okay, now I'm going to put something like this, delta x1 minus x2. Okay, so that is a function which, okay, pushes the particles apart. So this says 2 particles should not be in the same place, otherwise you have a bigger energy. Okay, so what happens to E1? Okay, for the ground state. How much will it change? Well, it's going to be equal to the H1. Now, okay, I have 2 indices for the state because both particles are in 1, 1. All right, and that means I'm going to get, okay, square of this, so it's going to be 4 over a, and psi 1, 1, 0, complex conjugate, x1, x2, h1 itself, alpha, delta, x1 minus x2, and psi 1, 1 again, 0, of x1 and x2. And now I have to integrate over dx1 and dx2. Okay? So what does this do? Well, refer to the delta function integral. Let's do the x2 integral first. That just puts x1 equal to x2, right? x1 equal to x2 means, okay, this becomes a cosine squared of x1. Cosine squared there, cosine squared there. So that's going to be equal to 4 over a squared, right? Square of that. So it's going to be 4 over a squared. Let me pull the alpha out. Minus a over 2 to a over 2. So it's a double integral in x1 and x2. And I'll end up with cosine to the 4th power pi over a x, doesn't matter, x1 dx1. Okay? So if you get cosine to the 4, what do? You expand it, right? You don't have to look for Legendre polynomials or anything, right? Those people who understand the joke will understand it. Okay? So cosine to the 4 is going to give me, okay, I'm out of time, but let me just write this down. Okay, so cosine to the 4 pi over a x1 is going to be, well, cosine squared pi over x1 squared. So that's going to be 1/2, 1 plus cosine 2 pi over a x1 squared. So that will be what? 1 over 4, 1 plus 2 cosine 2 pi over a x1 plus the square of that, which is another 1/2, 1 plus cosine 4 pi over a x1, right? So,
Where did that second one? Oh, all right.
okay. So this will integrate out to 0. That will integrate out to 0. So you have 3 over 4 times 1 over 4. Okay, just as an exercise, complete this because we have run out of time. And maybe I'll assign this homework so that, okay, I'll be sure. Okay, I'll let you go. So we meet again next week, this time again because there's a spring break, right? And then next week on Thursday, Friday, okay, we have the exam.